pure substance is the phase change. Okay, these two equations. Okay, if you want to use these two, one of these two equations to calculate the specific entropy change of an ideal gas, must be ideal gas. Okay, some people use this equation in quiz 3. That's why it's 0. Okay, and then that's for specific entropy change. Okay, that's for specific entropy change. And then CB, they assume constant. If the question doesn't particularly ask you to, not to assume constant CB, you can make this assumption. Okay? If the question doesn't say or don't assume constant CB, then you can. Yeah. But if you don't assume, you use 8.7 or whatever, and then the results will be more accurate. But this may not add mark for you. So just try to solve the questions as quickly as possible. And also, by now, you should be very experienced for exams. Do the questions you can finish quickly first, and don't leave them until time is over. Yeah. And then do this. You don't have to do 1, 2, 3, 4, 5 in order. You just pick up the ones you feel easier. And then you even don't need to put it in order in your exam book. Okay, I can figure that out. Okay, so that's for ideal gas. Just don't be confused by ideal gas and pure substances with phase change. I already mentioned about this. You need to understand, isentropic efficiency, and we know the isentropic efficiency, actual turbine in the compressor, the efficiency is less than 100%. It means the actual turbine will generate less power than the isentropic turbine does, and then actual compressors will consume more power than the isentropic compressor. Okay. For transient processes, okay, this is the same as closed system, right? The reason we can do that just because we assume that at any particular time, the inside system everywhere is uniform. It means the properties is the same everywhere. That's why we can integrate all the terms in the energy equation from the first law energy equation applied to the open system, and then the same for entropy change. Okay, so this is the same as the formula for closed systems, but the major difference is here and here. Okay, system entropy change, mass is not constant. Okay, mass is not constant. Surrounding entropy change, not only the entropy change due to heat transfer, but also the entropy change due to mass transfer. Okay, and in that case, and if it's water, you can find entropy value from the property tables in Appendix B by knowing two independent properties. If it's not, if it's ideal gas, if you want to use this one, then you have to group the terms for the same mass together, because this is a specific entropy change. Okay? And specific entropy change multiplied by that mass. You need to understand, if after the revision, by looking at this, okay, and by looking at this, I'm not sure if you will get the idea. I hope I've been worried too much. Okay, and then now we go to the cycle. We didn't start any cycle until we start the second law. Okay? And then we need to understand, the definition of engine efficiency, definition of the coefficient of performance. Quite often people are confused by these two concepts. Okay? One is for engine. Engine efficiency is less than 100%. And for heat pump, for refrigerator, the coefficient of performance, they are greater than 1. Okay? So quite often people even, from the previous exam papers, you can see quite often, the first question is about something like that. Because I thought that's an easy question. Quite often people just confuse. They treat heat pump as an engine, and then treat engine as normally just in one way. You treat the heat pump and the refrigerator as an engine. That's wrong. Okay, and we can't go through the details. The definition of the efficiency, definition of the coefficient performance, and how to use Carnot cycle to validate some claim. If like I mentioned, claims, what kind of engine efficiency, and you can use Carnot cycle to compare with that. Okay, and for heat pump, heat refrigerator, the same. Okay, and from here to here, that's the application of the thermodynamic temperature scale. Okay, and this can only be, this from here to here can only be used for reversible cycle, like a Carnot cycle. Okay, so don't apply this to your car engine. You will get the wrong answer. Okay, so this is all right. Yeah. And then that's all for Carnot cycle. Okay, coefficient of performance. And then also understand the schematic diagram like that. Okay. For power cycles, okay, for this part, and then second law statement, and also you won't be asked the question what's the second law statement, what's the principle of entropy increase, but we need to remember that. What's the principle of entropy increase? For any processes and cycles, the total entropy change must be greater than zero. Okay, in the real world. If it's equal to zero, it's a cycle or process close to a reversible process. Yeah. If it's negative, it's impossible. Okay. So if you told someone you have learned thermodynamics, and when people ask you what the principle of entropy increase, no, don't know, never heard about this, and people wouldn't believe you have learned thermodynamics. Okay. The cycles, I think, because we only have say 5 cycles. Okay, actually we learned in 4 weeks. Okay, Rankine cycle, refrigeration cycle, that's yesterday. Rankine cycle and Order cycle. Okay, Order cycle, we need to understand the application, the analysis of the cycle includes the first law application, second law application, and we need to understand how to calculate the net work. Okay. Let's have a look at what I got here. Maybe for Rankine cycle. That's the basic Rankine cycle. Okay, so it's 1 to 2, 2 to 3, 3 to 4, back to 1. Okay, so that's we need to understand. And this 3' just for showing superheated, steam. Okay. And then the one in the middle, the rectangular, that's the Carnot cycle. Okay, Carnot cycle, the cycle efficiency can be calculated from this temperature dividing this temperature, 1 minus TL over TH. Okay, and then the Rankine cycle, the cycle efficiency, we have to calculate the net specific work and the specific QH before we calculate the some efficiency. Okay, so all of this, I think this one doesn't have any. I haven't found any mistakes. Yeah, they're all right. Okay, so this and that from here to here, that's the application of the second law. Okay, for compressed liquid. Okay, for compressed liquid, we have TdS equals du plus PdV. The other one is TdS equals dH minus VdP. Okay? And then when the S is 0, like 1 to 2 is isentropic compression process. And then 0 equals dH minus VdP. That's how we can, and then integration from 1 to 2, that's how we can get the entropy changes equal to constant specific volume times pressure. Because in the compressed liquid region, we just, it's nearly incompressible. Okay, liquid is nearly compressed. But this one can't be used to any of the other processes. Okay, and then, so that's the major equations here. And also regeneration, okay? And what's the description of this cycle on the TS diagram? Okay, you may not be required to draw a diagram. Yeah, you may be, okay, for some of the cycles. But understanding the cycle described on the TS diagram, I think it helps you to understand all the processes and also the analysis and the calculation. Okay, so I didn't put the TS diagram for this system here, but just to try to understand. Yeah, draw by yourself. Okay, with the open style feed water heater, what's the TS diagram? With closed style, what's the TS diagram? But basically, the cycle efficiency can be calculated like that. Can be like that, can be like that. Okay? And how to use the tools, I think actually up to you. Okay? So here just present all the tools. You can bring all the tools with you on the A4 page, right? Yeah, and then you need to understand when you should use which one. And this part just to show, because that's the analysis of this open style feed water heater. Okay, so this equation shows how to determine the percentage of the steam which should be extracted from the turbine to the feed water heater to make up state 3. Okay, state 3 normally is saturated liquid. Okay, so this equation. And once you understand how to apply the first law to analyzing a open style heat exchanger, I think you understand this. Okay, you understand this. And also because the mass is not, if we say that's the unit mass of the steam, and after the first stage expansion, it's not 1 kilogram. Okay, so that's why I just listed the formula to calculate the turbine specific work, because the mass is not constant. Okay, it's not constant. And also for pump work as well. Okay, the first pump, I explained why we need 2 pumps. And if here is a closed style, we don't need 2 pumps, we need only 1 pump. And what's the reason? I think you need to go back to your notes. If you didn't write, then that's it. Okay, and then gas turbine. Gas turbine is only the thermal efficiency. Okay, we have looked at thermal efficiency. Thermal efficiency is only a function of the pressure ratio in the compressor. Okay, if it basic Brayton cycle, not the Brayton cycle with regeneration. Okay, if there is a regeneration or whatever, it's not standard, not basic Brayton cycle, then we can't use this one. Okay, that's explained what's the pressure ratio. If we are asked to find out cycle efficiency, and that's the formula. Okay, the same to all the engines, and that's the application of all the first law, second law to the 4 processes. And here again, because the compression process is isentropic, because the working fluids can be assumed as ideal gas. That's why we can do like that. Okay, and then that's based on the assumption, because for Brayton cycle, remember the general one of the assumptions is CP/CV, they're constant. Okay, CP/CV constant. If the CP/CV are not constant, then enthalpy and internal energy will be functions of temperature. They are functions of temperature. Okay. And all these four processes, I think probably we don't have time to go through the details. Otherwise, we just repeat the lecture. And here, I just want to mention about for Brayton cycle with regeneration. Okay, and regenerator normally has efficiency less than 100%. That's that's the final formula. It's not the definition. The definition is based on the comparison between the energy change in the regenerator and compared with perfect regenerator. Okay, but finally, and we assume constant CP. That's why enthalpy change becomes temperature change. And here, I still kept x prime here. I didn't replace by this one because this is depends on isentropic process or irreversible. If this is irreversible, okay, and then x prime, I put the s here, okay, x prime will be here. Okay, if it's irreversible, okay, and if it's irreversible, okay, like this, that one, just leave it like that. And that's the formula to calculate the efficiency of the regenerator. Okay, and with the application by installing the regenerator, the QH will be reduced. Okay, the power generated by the turbine, the power consumed by the compressor won't be changed. Okay, only the QH because QH is reduced. That's how the efficiency is increased. And then Otto cycle and the diesel cycle. Okay, Otto cycle is for spark ignition engines, and the diesel cycle is for compression ignition engines. Okay, and here, similar to the Brayton cycle, the cycle efficiency of Otto cycle must be Otto cycle. It's only a function of the compression ratio. Okay, compression ratio. Normally, we only care about displacement, right? Actually, the compression ratio is the key point for efficiency. Okay, but no one would care about the clearance volume. Yeah? Like the sports car, okay, the clearance volume is very, very small. Yeah, just because they need the high compression ratio. And then this one is similar to all the other engines, the cycle efficiency. And don't be confused by processes and cycles. Some of the cases, just like increase 3, the question is about expansion process, okay, not a cycle. And some people just use the formula for cycle for power cycle efficiency. So that's why I can't find the information. Because just wrong tool. Yeah. You pick up the wrong tool. Okay. And also, the application of first law and second law, the major difference between this cycle and the other power cycles is this cycle is assumed happening in a closed system. Okay? All the other cycles, they involve steady state, steady flow process. But this cycle involves constant volume process, constant pressure process in closed cycle, closed system, okay, closed system. That's why here is internal energy. I just highlight because it's closed system, okay. And so I just leave that to you. And then the major difference between the Otto cycle and the diesel cycle is the heat addition process. In the Otto cycle, here is a constant volume heat addition process, and in the diesel cycle, it's a constant pressure process. That's why diesel engines can have higher compression ratio. Okay, but for a diesel cycle, the cycle efficiency is not only a function of compression ratio, but also compression ratio here, but also a function of the current ratio.